Jai Hind everyone. This is Jyoti Sharma once again going to take certain lectures on the topic electrical machines, which is from unit 4 of the subject basic electrical engineering, having the subject code of KW 101 or 201 according to AKTU. Okay, so in electrical machines we have done the working, the construction, the characteristics for DC machines, motors and generators. Then in the previous lecture we have started with three-phase induction motor, which is an AC motor, which is also being called as a synchronous motor. We have discussed what is its applications. We have discussed what is the working principle for a three-phase induction motor, that is rotating magnetic field. How this rotating magnetic field is being produced, as we used to give the AC supply to the stator windings, the three-phase stator windings, right? So we have also seen in construction that how the stator looks like and how the stator is being made up of various stampings, and in that we used to have three-phase being connected either in star or in delta. Three-phase winding used to be there. Now we'll be starting with the rotor construction of the three-phase induction motor. Then we are going to study what is slip and its effect on the various rotor parameters, right? Then the torque equation for a three-phase induction motor and torque slip characteristics. Quickly moving on to the construction of rotor. Now, as you can see, the construction of the rotor, here, the rotor is also built up of thin laminations of the same material as that of stator, right? So the laminated cylindrical core is mounted directly on the shaft. These laminations are slotted on the outer side of to receive the conductors, right? These are the slots, if at all I say. So here I used to have slots, right? Then there are two types of rotor. One is the squirrel cage rotor and the another one wound rotor, or it is also being called as slip ring rotor, right? First, going for the squirrel cage. As the name is suggesting, a squirrel cage rotor consists of laminated cylindrical core. The circular slots at the outer periphery are semi-closed, right? What we were just discussing. These are semi-closed, right? Each slot contains an uninsulated bar conductor of either aluminium or copper, right? These are the aluminium bars or the copper bars, what can be seen, right? If you can see, these are not exactly the straights. These are a bit screwed, right? Slightly screwed. At the end of the rotor, the conductors are short-circuited by a heavy ring of copper or aluminium. This heavy ring of copper or aluminium, this is being called as end ring, right? That's why this kind of construction, a squirrel cage rotor construction, forms a short-circuited rotor construction, right? The rotor circuit is a short-circuit rotor, right? The rotor slots are usually not parallel to the shaft, as I just told you. These are a bit screwed. The screwing of the rotor conductors, it doesn't have certain advantages. Likewise, it used to reduce the humming and provides a smooth and noise-free operation. It results in uniform torque curve for different positions of the rotor. The locking tendency of the rotor is reduced, right? The locking between the stator magnetic field and the rotor, right? As the teeth of the rotor and the stator attracts towards each other and they used to lock, right? So this locking tendency is being reduced. It also increases the rotor resistance due to the increased length of the rotor bar conductors, right? Now, the advantage of this squirrel cage rotor is this kind of rotor is having a robust construction. It is also cheaper, right? It doesn't have to have brushes. It doesn't have to have the slip rings. So, if it doesn't have a brushes, so it reduces the risk of sparking. It doesn't have slip rings, so it reduces the maintenance cost, right? The power factor is comparatively higher and the efficiency of the cage rotor is also higher, right? Compared to the slip ring one. or the phase wound rotor. So this is the second kind of rotor. This is phase wound rotor, or also being a slip ring, as it used to use slip rings at the end. Here, these are the slip rings. So the phase wound rotor, as it is being saying phase wound, it is being wound, right? It is also being called a slip ring. It consists of cylindrical core that is laminated. The outer periphery of the rotor has a semi-closed slots that carries a three-phase insulated windings, right? Instead, in case of squirrel cage, these unslotted, the semi-closed slots, they used to have a long aluminium copper bar or aluminium bars or copper bars running throughout the length, right? Whereas here we used to have the rotor used to be wound in a three-phase fashion, right? Either star or delta. So the rotor windings are connected likewise exactly the same way as the stator is being wound. If the stator is being wound as star, then the rotor will also be wound for star. And if it is being wound for a delta, then the rotor will also be wound for a delta, right? So the slip ring induction motor, it can be seen in the diagrams. So they are mounted, the slip rings, the slip rings are mounted on the shaft with the brushes resting on them. So this is a slip ring and brush assembly which is being used. The brushes are connected to the variable resistor. The function of the slip rings and the brushes is to provide the means of connecting external resistors to the rotor circuit. And this function, this particular function which is being done by the slip ring and brush assembly cannot be accomplished in case of squirrel cage, right? Because there we used to have a short-circuited rotor circuit, right? So there is no any provision to get an external resistance being added to it. But why do we want to have an external resistance being added to the rotor circuit? We can be directly short-circuiting them with the ends, right? But we'll be seeing that the addition of the external resistance to the rotor circuits helps us in many ways, right? What does it do? It used to increase the starting torque of the induction motor. We can be having a varying starting torque, in fact an increased starting torque, right? We can have one of the methods of the speed control of the induction motor, and also we can always be, the inrush current of a three-phase induction motor, as the reactance is very low, the resistance is very low. At the starting, there used to be a very heavy inrush current of the current when you switched on the three-phase induction motor. To reduce that inrush current, we may even increase the rotor resistance, right? There are many ways, we can be starting it by using auto transformers, by reducing the voltage, V by F method, and various methods by which we can be giving our a star delta or direct online starters. There are many ways by which we can in fact start the three-phase induction motors, but one of the ways is by using or by adding extra resistors to the rotor circuit, right? So that the inrush current is reduced. Okay. Now the resistor enables the variation of each rotor phase resistance to serve the following purposes. As I was discussing, it increases the starting torque, decreases starting current, it used to control the speed, right? Likewise in the stator, here also the rotor is skewed. A mild steel shaft is passed through the center of the rotor and is fixed to it. The purpose of the shaft is to transfer the mechanical power. The advantages, if you just see, obviously high starting torque and low starting current. And for controlling the speed of the motor, and external resistance can be added to it. These are the advantages which are absent in case of squirrel cage induction motor, right? Now, coming to, we have now discussed the construction, the working principle, rotating magnetic field, how it is being produced, right? So now, why can't we just put that and make a proper working of a three-phase induction motor? We can explain it, right? Say, consider a portion of three-phase induction motor, right? So the operation of the motor can be explained, with the very first step is, when a three-phase stator winding is energized from a three-phase supply, what will be happening? A rotating magnetic field is set up, which rotates round the stator at synchronous speed. That synchronous speed is given by 120 F by P. We have discussed that. We have seen how the three-phase AC supply is able to produce a rotating magnetic field, right? Now, this rotating field, when passes through the air gap and cuts the rotor conductors, which are yet stationary. The rotor is not rotating right now, right? So, the rotor conductors are stationary. Due to the relative speed between the rotating flux and the stationary rotor, what is going to happen? The EMF is going to get induced in the rotor conductors. Since the rotor circuit is short-circuited, right, either with the help of the end rings or with the external rotor resistors, right? So, the current starts to flow in the rotor conductors. Now, what is happening? Now, I am having a current carrying rotor conductor placed in the magnetic field produced by the stator. So, what is going to happen? There will be a mechanical force which will be acting on these rotor conductors. The torque would be produced. The sum of the mechanical forces on all the rotor conductors produces a resultant torque which tends to move the rotor in the same direction as that of the rotating field. Why? We have discussed that. The fact that the rotor is urged to follow the stator field, that means the rotor moves in the direction of the stator. That can be explained by Lenz's law. According to Lenz's law, the direction of the rotor currents would be in such a way that to oppose the cause producing them. And what is the very cause producing them? The cause producing the currents is the relative speed between the rotating magnetic field and the stationary rotor conductors, right? Now, the torque would be produced in such a way that they can reduce this relative speed. So, the rotor will try to rotate in the same direction as that of the stator magnetic field and also tries to attain it, right? And if at all it attains it, what is going to happen? If at all it attains it, what is going to happen? If at all it attains the synchronous speed, then there will not be any relative motion between the two. If there is no relative motion between the two, then there will not be any flux cut, there will not be any induced EMF, there will not be any current, and there will not be any torque. So, the motor will ultimately come to rest. Okay. Now, when the motor has come to rest, once again the same process will start. Now, once again, what is the relative motion? I am having the stator magnetic field, right, rotating at a speed of ns, and the rotor conductors are now stationary. So, what is going to happen? Once again, I am having the maximum relative motion between the two, so that now once again, I will be having a flux cut, thereby EMF, thereby current, and thereby torque, and once again the rotor will start to rotate. So, the rotor is going to do the same, is it? It is going to start, stop, start, stop? No. Because of the inertia of the motor, it doesn't start, right? It used to be at, it used to be running, but what it used to do? It used to start, it used to follow the speed of the synchronous, but it never attains the same speed, right? It always used to run at a speed which is slightly lesser than ns, which I call it as sub-synchronous speed or asynchronous speed, right? So, that speed is slightly lesser than ns. The difference between the synchronous speed ns and the speed of the rotor, that is being called as slip, right? So, the next very topic what we are going to get discussed is slip. So, what we have just arrived at a conclusion that a three-phase induction motor will never be running at ns. It will try to attain the same speed, but it will always be running at a speed which is slightly lesser than ns, right? And the difference between these two is given by the slip speed. That means ns minus nr, where ns is the synchronous speed 120 f by p and nr is the speed of the rotor, or I may be saying the speed of the motor, right? The difference between these two gives me the slip speed, and when this is being expressed as a fraction of the synchronous speed, that is being given as slip. It is denoted by the letter S. So, that is ns minus nr upon ns. It is also being called as n. Many of the times the notation is also n. So ns minus nr upon ns gives the slip. Percentage slip can be given by multiplying it with 100. Right. The thing to remember is the quantity ns minus n is called as slip speed. When the rotor is stationary, that means the speed is 0. At that time, at the starting, the slip value would be 1 or 100%. In an induction motor, the change in the slip from no load to full load is hardly from 0.1 to 0.3%, so that it is essentially a constant speed motor. Right? Okay. Now, what are its effects? The effect of rotor of the slip on rotor current and rotor current frequency and various other rotor parameters, right? So, let's go for that. The frequency of the voltage or the current induced due to the relative speed between the windings and the magnetic field is given by the general formula, right? So, where n is the relative speed between the magnetic field and the winding and p is the number of the poles. For a rotor speed n, the relative speed between the rotating flux and the rotor is obviously ns minus n. So, consequently, the rotor current frequency is given by, at starting, f is given by, what is the speed? That is ns, right? Which is given by 120 f by p. At some rotating condition, what I'm having it as the slip speed, I'm having it as ns minus n. So, that is given by some 120 f dash upon p, isn't it? So, f dash is given by some ns minus n into p upon 120, right? So, just opening it, once again just substituting s or ns minus n. Right. So, I'll be having that f dash is equals to s times of f. That means that the rotor current frequency is the slip times the supply frequency. Right. So, that is the very first parameter that is going to get changed. This is the frequency of the rotor currents. This is the frequency of the rotor induced EMF. Right. Okay. Now, other. Likewise, rotor induced EMF, as I just told you, as the frequency of the rotor currents is changing, the frequency of the rotor induced EMF will also change and the induced EMF will also change, right, in the rotor. So, supposingly, if at all I just say that, because we know that induction motor is very much analogous to a transformer. Both of them works on the same induction principle, right? In transformer, we used to have primary and secondary winding. In case of induction motor, we used to have stator and rotor windings. So, the stator is very much identical to a primary and rotor is very much identical to a secondary, right? So, the notations what we used to use for transformer, the same notations we can be going on for here. For the primary circuits, I'll be using a suffix of 1, likewise E1, R1, F1, right? Likewise, I1. Similarly, the 2 suffix would be used for rotor parameters. Likewise here. E2, that is nothing but the rotor induced EMF per phase on standstill condition, right? Standstill condition where the rotor is not moving. At that time, what is going to be the rotor induced EMF? E2, which is proportional to the slip speed. And what is the slip speed at standstill condition? It is just ns because the speed is 0, which is equals to 120 f by p. Now, supposingly E2R, that is the rotor induced EMF per phase in running condition. That means with certain slip S. So, this time this E2R must be proportional to what? The slip speed. And what is the slip speed now? Ns minus S. That's what I was saying. E2 is proportional to Ns and E2R is proportional to Ns minus N. If at all I take the ratio of the two, once again I'll be deriving or I'll be achieving that the rotor induced EMF per phase in running condition is equals to slip times the rotor induced EMF per phase on standstill condition. Rotor resistance and reactance, right? Rotor resistance per phase on standstill condition, if that is given by R2, is it going to get changed in running condition? No. Why? Because rotor resistance is not a frequency dependent parameter, right? According to the frequency, there is not going to be any change in the rotor resistance. So if at all I say R2 is the rotor resistance in ohms per phase, either in standstill and even in running condition, right? If X2 is the rotor reactance per phase on standstill condition, then definitely I can be giving X2 as 2 pi FR L2, right? Or 2 pi F L2 ohms per ohms, fine, per phase, right? Now, what about X2R? What is X2R? That is the rotor reactance under running condition. Once again, the formulation is 2 pi FRL, but this time FR is changed. At running condition, what is FR? FR is S times of F. So, just substitute that, right? So, that is 2 pi S times of F L2. So, that becomes S times of 2 pi L2 or S times of X2. So, once again, the rotor reactance in running condition is equals to the slip times the rotor reactance in standstill condition. Similarly, I may even give the expression for rotor impedance in standstill condition Z2. That has to be R2 plus JX2, obviously ohms per phase, right? Just substituting for R2 and JX2, X2 can be given as, or I may even, because here I do not require any S and all that, so I can be directly give it as under root of the magnitude of the rotor impedance can be given as under root of R2 square plus X2 whole square ohms per phase. Now, if Z2R gives the rotor impedance in running condition, that can be obviously given by this time. Rotor resistance is not going to get changed. We have seen that, but the rotor reactance, that has to be X2R. Substituting for X2R, that is S times of X2. Substituting, Z2R would be given by under root the magnitude under root of R2 square plus Sx2 whole square ohms per phase. We need to remember this when we are finding the torque equation. Finally, the rotor power factor. Cos phi 2, the rotor power factor on standstill condition, right? Cos phi 2, that is R2 by X2 given by R2 upon under root of R2 square plus X2 whole square. We know that, right? No changes in that at standstill condition. But in running condition, once again, R2 upon Z2R. Z2R, the value is going to change by under root of R2 square plus Sx2 whole square, right? Finally, the rotor current. Once again, the rotor current I2, that is given by E2 per phase by Z2 per phase, right? E2 per phase is this, Z2 per phase, this is in standstill condition. So, that will be given by under root of R2 square plus X2 whole square, right? But I2R, rotor current per phase in running condition, would be given by E2R upon Z2R. E2R is given by S times of E2, Z2R is given by under root of R2 square plus Sx2 whole square. Going for the numericals, based on what we have discussed till now. A 3-phase induction motor is supplied at 50 Hz and is wound for 4 poles. Calculate the synchronous speed, the speed when slip is 3%, frequency of the rotor EMF when it runs at 1200 RPM. So, it is very simple, right? The 3-phase induction motor is supplied with 50 Hz, it is wound for 4 poles. So, we need to calculate the synchronous speed given by 120 F by P, where F is the frequency given by 50. So, that is 120, 50 upon P is just 4. So, that is going to be 1500 RPM. Second is the speed when slip is 3%, right? So, we know that the speed is given by Ns into 1 minus S, where S is the slip. So, just substituting this as 3%, that is 1500, 1 minus 0.03, that is going to get 1455 RPM. Third one, the frequency of the rotor EMF when it runs at 1200 RPM. So, that is going to be S times of F, that is 0.0, frequency of the rotor induced EMF when it runs at 1200 RPM, right? So, here the speed has been changed to 1200 RPM. So, for this, a new slip is to be found out, right? So, for this, the slip can be found out as Ns minus Nr upon Ns, right? So, the new slip where this Nr is going to be 1500 minus 1200 upon 1500. So, the now slip is going to be 0.02. So, Fr is going to be S times of 50, that means 0.02 into 50, that is going to be 10 Hz. Another one, for a 4-pole Three-phase 50 Hz induction motor. The ratio of stator to rotor turns is 3. On a certain loads, its speed is observed to be 1450 rpm when connected to 415 volt supply. Calculate. First, the frequency of the rotor EMF in running condition means what I'm asking for? FR, right? So, I'm asking for FR. Then the magnitude of the induced EMF in the rotor at standstill. What I'm asking for? I'm asking for E2. And the magnitude of the induced EMF in the rotor under running condition, assuming to be the stator to be star connected. I'm asking you E2R. Okay, so the given informations to us is the number of poles is 4, frequency is 50 Hz. E1L, the stator input voltage, the line value, that is going to be 415, right? The turns ratio, rotor turns to stator turns, that is going to be, it has already been given to us that the ratio of stator to rotor turns is 3. So, rotor to stator turns is going to be 1 by 3.033 and the speed of the motor is 1450. So, the very first thing what we are going to calculate is FR, the frequency of the rotor EMF in running condition given by S times of F. We already know how much is the slip, right? How much is the slip? That can be found out by Ns minus Nr upon Ns. Ns can be easily found out, that is 1500 because it is a 4-pole 50 Hz. In the previous numerical also we have found out for a 50 Hz 4-pole induction motor, the synchronous speed is going to be 1500 rpm. The speed is 1450. So, that can be very easily known. So, that is 1500 minus 1450 upon 1500. So, that is going to be 0.33 into 50. So, that is 1.66 Hz. Now, we need to know E2 per phase. Obviously, it is the induced EMF in the rotor at standstill, that is E2 per phase, right? So, we want to have the phase value of it. So, what's its relation? Directly I can't be knowing. I first need to know even per phase, right? Stator voltage per phase, multiply it with the turns ratio, right? Once again, for knowing the phase value of the stator voltage, I need to first, the relationship. It is a star connected system. The stator is a star connected system. In a star system, the phase voltage is line voltage by root 3 times. So, the line voltage by root 3 times multiplied by K. Line voltage, that is 415 by root 3, that is 239.6 divided by root 3. So, that is going to be 79.78 volts, right? Okay, then finally, E2R. E2R is nothing but the S times of E2 per phase. So, that is S is 0.33 multiplied by 79.78, that is going to be 2.63 volts. So, I suppose we should be continuing this lecture with the torque slip characteristics, the torque equation, the torque slip characteristics and its applications in the next of the lecture. Thank you all.